So last period we have discussed about DM, that is delta modulation. Now we are going to discuss about the adaptive delta modulation. That is ADM. The delta modulation, the main concern was about the step size. Step size avada fixed aayirunnu. So step size selection എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ഇറ്റ്സ് എ മേജർ റിസ്ക് ആണ്. കാരണം സ്റ്റെപ്പ് സൈസ് കൂടുതലാവുമ്പോൾ ഇറ്റ് ലീഡ്സ് ടു ഗ്രാനുലാർ നോയ്സും ആൻഡ് സ്റ്റെപ്പ് സൈസ് കുറവാകുന്ന സമയത്ത് ഇറ്റ് ലീഡ്സ് ടു സ്ലോ പവർ ലോഡ് ഡിസ്റ്റോർഷൻ. ഇങ്ങനത്തെ രണ്ട് ടൈപ്പ് ഡിസഡ്വാൻറ്റേജ് ഉണ്ടായിരുന്നു. This was due to the step size selection. To overcome this, that is the demerits of this delta modulation, this adaptive delta modulation was introduced. In this ADM, here step size is not fixed. It is varied according to the as per the input signal. If the input shows a steep variation, that is, if the input shows a steep variation, step size is increased, that is delta is increased. And if the input is slowly varying, that is, input is flat type input, then step size is reduced. That is, it is varied according to the input signal, not like in delta modulation in which step size is fixed. In ADM, step size is not fixed, it is varied according to the input signal. If the input is a steep signal, then the step size delta is increased, and if the input is flat, the step size delta is decreased. Now we will go to the ADM transmitter. This ADM transmitter is very similar to delta modulator, but there is a logic circuit to control the step size in ADM transmitter. Here, the input X of NTS is our input, which is given to a comparator. Here, we have a delay circuit of time period TS, and it is given to 1-bit quantizer, as in case of delta modulator. And the output B of NTS, and it is given to a summer, and this is our delayed version, and this is our X cap of NTS, and this is our E of NTS, which is the error signal, and this is our delta modulator transmitter. Now in the case of ADM transmitter, the only change which comes is then there is a block called logic for step size control. That is, here we have a block logic for step size control. This is introduced in this ADM. In ADM we have a logic for step size control. This is the only difference in delta modulator and ADM. And rest all are same as per the delta modulation. Now in ADM receiver, going on to the ADM receiver, this logic for step size control decides the step size based on the input signal. Input എങ്ങനെയാണോ, input steep ആണെങ്കിൽ delta value നമ്മൾ high ആയിട്ട് എടുക്കും. Input flat ആണെങ്കിൽ, അതായത് വേരിയേഷൻ വളരെ കുറവാണ്, സ്ലോലി വേരിയിങ് ഇൻപുട്ട് ആണെങ്കിൽ സ്റ്റെപ്പ് സൈസ് ലോജിക് ഫോർ സ്റ്റെപ്പ് സൈസ് കൺട്രോൾ സ്മോൾ ഡെൽറ്റ വാല്യൂ ഡിസൈഡ് ചെയ്യും. ആൻഡ് ഗോയിങ് ഓൺ ടു ദ ADM receiver, we have input and we have a logic for step size control. Step size control whose output is given to our accumulator side, same as that of the delta modulator receiver. We have a low pass filter and we have the output. The only changes in the receiver, there is a extra block called logic for step size control in the receiver side. ഇത്രയാണ് ഇതിന്റെ ഡിഫറൻസ്. റെസ്റ്റ് എല്ലാ വർക്കിംഗ് പ്രിൻസിപ്പിൾ സെയിം ആസ് ഓഫ് ഡെൽറ്റ മോഡുലേഷൻ ആണ്. The only difference in adaptive delta modulation എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ compared to delta modulation is that we have a logic for step size control. അതായത് step size is varied here in ADM. Step size എന്ന് വെച്ചാൽ it's varied as per the input signal, not like in delta modulation. And the problems in delta modulation like slope overload distortion and granular noise was eliminated or avoided in this adaptive delta modulation. Now we will discuss about the advantages of this adaptive delta modulation. That is, advantages of this adaptive delta modulation. Here, the main advantage for which it was introduced is to avoid the slope overload distortion and granular noise. So this will be the first advantage, that is slope overload distortion and granular noise is reduced, and hence we have a better signal to noise ratio. This is the first advantage. And second is wider dynamic range of input is possible which was not possible in delta modulator. That is, we have a wider dynamic rate of input possible compared to delta modulation. Due to here we have a variable step size, we can choose the step size as per the input range. So it supports wider dynamic range of input. And the last one is better utilization of bandwidth compared to DM. That is, compared to delta modulation, it have better utilization of bandwidth. First one was slope overload distortion and granular noise get reduced, and hence it increases the signal to noise ratio. And second one is wider dynamic range is possible here, which was not possible in delta modulation due to its fixed step size, whereas in ADM the step size is variable. So wider dynamic range of input is possible in ADM. And third advantage is that better utilization bandwidth compared to DM. Is that clear? Is it clear or no? Now we'll discuss about the AD-PCM. We have discussed about PCM, DPCM. Now we will discuss about that. And first we have started with PCM, then DPCM, then delta modulation, then ADM, that is adaptive delta modulation, and last one is adaptive differential pulse chord modulation, that is AD-PCM. Here it is a combination of both adaptive quantization and adaptive prediction. That is, this ADPCM uses both adaptive quantization and adaptive prediction. And adaptive quantization refers to the quantization. Adaptive quantizer, it refers to the quantizer that operate with varying step size. And this adaptive prediction means same as differential pulse code modulator prediction. This adaptive ADPCM prediction. Oh, sorry, DPCM. Adaptive prediction and adaptive quantization. Now going on to the ADPCM transmitter. We have X of NTS, which is given to a quantizer. Prediction filter. Here we have a logic for step size control. The difference between the actual sample value or the sample value and the predicted value X of TS is known as prediction error. This is our prediction error, E of NTS. That is, E of NTS is nothing but X of NTS minus X cap of NTS. So this is the transmitter side of adaptive differential pulse code modulation, same as DPCM. Here we have a logic circuit for deciding the step size. So adaptive quantization in the sense that, which we have in the case of ADM, we can select the step size, and rest all are the same as that of DPCM. Here DPCM same based on prediction, and the only extra thing here comes is the logic circuit for step size selection, and so that we can select the step size as per the varying input. And in the receiver, this is the transmitter side. The DPCM is block diagram, but only an extra circuit is there, or extra block is there for logic circuit for step size selection. Now we will go to the receiver side. Here, ADPCM output, it's given as an input to this inverse adaptive quantizer, which is then given to an adaptive predictor. Instead of predictor, an adaptive predictor. Then estimate is given to this predictor. Signal estimate. PCM. So ADPCM signal is given to an inverse adaptive quantizer, and the output is given to a summer, in which the input to the summer is the output from inverse adaptive quantizer and adaptive predictor, and the output we get the PCM signal, that is pulse coded signal. This is about the receiver side of this ADPCM. Now before going on to the line code, we will just compare performance or comparison of various pulse code modulation scheme. We have first studied about PCM and delta modulation, ADM, DPCM, DM and ADM. Performance wise comparison ആണെങ്കിൽ number of bits in PCM 4, 8, 16 bit ആണ്. And DPCM എന്ന് പറഞ്ഞാൽ more than 1 bit but less than PCM. And DM le 1 bit per sample and here 1 bit per sample. Here 4, 8, 16. Here in DPCM more than 1 bit ആണ്. That is more than 1 bit and less than PCM ആണ്. And next is about the number of level and step size. Here number of level depend upon the number of bits step size, and here step size is fixed in DM. ADM we have variable step size. Here we have a fixed number of level. Here also step size is fixed and it depend upon number of level depend upon number of bits. Here number of bits in here bit rate high bit rate ആണ്. So step size കൂടെയുള്ളൂ. Number of bits depend upon number of level but step size is fixed. Here in DPCM fixed number of levels ആണുള്ളത്. And in delta modulation also fixed number of levels ആണുള്ളത്. That is step size fixed ആണ്. And ADM ൽ മാത്രമേ variable step size ഉള്ളൂ. Here this quantization error depend upon number of level, and the quantization error in case of DM depend upon the slope overload distortion error and granular noise. And in case of ADM the quantization noise present, other error absent. And in DPCM slope overload distortion and granular noise present. And in the case of transmission bandwidth, here high transmission bandwidth and DM has the lowest transmission bandwidth, and ADM also have lower bandwidth. The here bandwidth is lower than PCM. So comparing bandwidth, PCM has high bandwidth and lowest bandwidth is obtained in delta modulation and ADM. And DPCM the bandwidth is less than PCM but not less than the delta modulation and ADM. Telling about the feedback, there is no feedback in transmitter and receiver in PCM, no feedback. In delta modulation there is feedback in transmitter side, and in ADM also feedback is present, and DPCM also feedback is present in the sense that we are taking the output from prediction filter. And complexity of implementation, here implementation is a complex and rest all the cases are simple implementation. PCM complex implementation ഉള്ളത്, ബാക്കി എല്ലാത്തിനും simple implementation മാത്രമേ ഉള്ളൂ. Comparison I will provide the notes, അത് നിങ്ങൾ go through ചെയ്താൽ മതി. This is about the comparison of various pulse code modulation technique. Next we are going to discuss about the line code, which is the last topic in the first module. So This line code, what it do is, it convert the bit stream 0, 1, 0, 1 into this waveform. That is, these line codes are used for electrical representation of binary data stream. These line codes are used for electrical representation of binary data stream, and we have 4 or 5 types of line codes. One is unipolar, non-return to 0. Then we have polar, non-return to 0. Then we have unipolar, return 0. Then we have bipolar, non-return to 0. Then we have Manchester code. These are the 5 line codes we have. In unipolar, we have 2 values, either 0 or 1. That is 0 or voltage level, 0 or 1. So here in unipolar, symbol 1 is represented by transmitting a pulse of amplitude A for the duration of the symbol, and symbol 0 is represented by switching off the pulse, and it is called on-off signaling. Here in unipolar non-return to 0, we symbol 1 transmit by transmitting a pulse of amplitude A amplitude a pulse transmit 0 by represented by switching off the pulse. Here 0 is transmitted by switching off the pulse, and A1 it's transmitted like this, and next also it's 1 transmitted or amplitude A ulladu. Next is 0, which is here again 1, 0, 0. Again 1. So here in unipolar non-return to 0 signaling, it is also known as on-off signaling. Here 1 is represented by transmitting a pulse of amplitude A for the duration of the symbol, and 0 is represented by switching off the pulses. Here we have a 0 which is off signal, and here it is on signal, and I have an amplitude A. So it is also known as on-off signaling. Unipolar non-return to 0 is also known as on-off signaling. And next we will discuss about the disadvantage of this unipolar non-return to 0, the waste of power due to transmission of DC level. DC level transmit. So I DC level that's a waste of power. So waste of power is a disadvantage of this unipolar non-return to 0. Next is polar return to 0 signaling. Here symbol 1 and 0 are represented by transmitting a pulse of plus A and minus A respectively. Here symbol 1 is represented by positive A and symbol 0 is represented by negative A. So first one is symbol 0, so negative A, followed by symbol 1 which is positive A, and again symbol 1 positive A. So next is 0 which will be negative A, and again symbol 1 which will be positive A, negative A, negative A, and positive A. This is polar non-return to 0. Here symbol 1 transmit the positive A which symbol 0 transmit the negative A. So here first one is 0, so negative A. Next one is positive 1, that is positive A, negative, like that. And ഇത്രയും മനസ്സിലായോ? ഇത് മനസ്സിലായിനോ? ഓക്കെ. ഇനി നെക്സ്റ്റ് യൂണിപോളാർ നോൺ റിട്ടേൺ ടു സീറോ. നെക്സ്റ്റ് കേസാണ് യൂണിപോളാർ റിട്ടേൺ ടു സീറോ. സോറി, റിട്ടേൺ ടു സീറോ. ഇതാണ് നോൺ റിട്ടേൺ ടു സീറോ. ഇനി റിട്ടേൺ ടു സീറോ. Here in the case of unipolar return to zero, symbol 1 is represented by a rectangular pulse of amplitude A and half width. Here in unipolar return to zero, symbol 1 നമ്മൾ represent ചെയ്യുന്നത് of amplitude A, that is amplitude A and half width of the symbol. ഇത് ഈ ഒരു 1 എന്ന് പറഞ്ഞ സിമ്പിളിന്റെ this is the full width. അതിന്റെ half width വെച്ചിട്ട് നമ്മൾ represent ചെയ്യുക. Symbol 1 is represented by a pulse of amplitude N A and half width. ഈ ഒരു സിഗ്നലിന്റെ half width വെച്ചിട്ട്. And symbol 0 is transmitted by transmitting no pulse. Symbol 0 എന്ന് പറഞ്ഞാൽ ഒന്നും ട്രാൻസ്മിറ്റ് ചെയ്യാണ്ട് നിൽക്കുക. So here we have one and here we have another one. Here we have one which is a pulse of A and half width. Here also. ഇതാണ് unipolar return to zero. Symbol 1 എന്ന് പറഞ്ഞാൽ it will be a pulse of amplitude A and half width of the symbol. ഇതിന്റെ half width. And symbol 0 transmit ചെയ്യുന്നത് by transmitting no pulse. So ആ DC power wastage നമുക്ക് ഇവിടെ reduce ചെയ്യാൻ പറ്റും. And next is bipolar non-return to zero. ഇതിന്റെ കേസിൽ here 3 amplitude level ഉണ്ട്. The positive and negative pulse are used alternatively for symbol 1. Here symbol 1 transmit ചെയ്യാൻ same as that of unipolar return to zero. Here bipolar non-return to zero നമ്മൾ first symbol 1 ഇപ്പൊ ഇങ്ങനെ ട്രാൻസ്മിറ്റ് ചെയ്ത് കഴിഞ്ഞാൽ second will be like this of amplitude A. The second symbol 1 will be alternately changed. But third one will be like this and next one will be like this. Here positive and negative pulse of equal amplitude, that is positive and negative pulses of equal amplitude are used alternatively for symbol 1. So if positive pulse is used for first symbol 1, then for the next one negative pulse will be used, and for the next again positive, and for next negative, like that it will be used alternately. And each symbol will be having half symbol width, as in case of this half symbol width ഉണ്ടാവുക, and amplitude will be A. This is about bipolar non-return to zero. And last one is the Manchester coding. Here if it is 0, 1, 1, 0, 1, 0, 0, 1 ആണെങ്കിൽ ഈ മാഞ്ചസ്റ്റർ കോഡിങ്ങിൻ്റെ അകത്ത് zero, if it is represented by like this, means 1 is represented like this. Appo if 0 is represented, first one is 0, which is represented like this, and next one is 1, so will be like this, and next also is 1, so it will be like this. And next one is 0. So like this. 0 means like this, 1 means like this. So again 1, again 0, so again 0. അതായത് 0 എന്ന സിമ്പിൾ ആണെങ്കിൽ ട്രാൻസ്മിഷൻ will be like this, and 1 ആണെങ്കിൽ like this, again 1, so like this, so 0 followed by 0, and again 1, 0, 0, and again 1. Is that clear? This is Manchester coding. And this is also known as split phase. This Manchester coding is also known as split phase. Here symbol 1 is represented by a positive pulse of amplitude A followed by a negative pulse of amplitude minus A with half symbol period width. And for 0 polarity, this pulse are reversed. 0 polarity, this pulse are reversed. മനസ്സിലായോ? അല്ലേ ഒന്നും കൂടി പറയണോ? ഒന്നും കൂടി പറയണോ? ഓക്കെ മനസ്സിലായി. ഇതാണ് ലൈൻ കോഡ്സ്. നൗ ടുമോറോ വിൽ ലേൺ അബൌട്ട് ദ പവർ സ്പെക്ട്രം ഓഫ് ലൈൻ കോഡ്സ്. PST for each of these line codes will be